Thanks for the brief introduce. And so I'm Zhang, and currently the third-year computer science PhD student at the uni. So working with the AI for Biomedical lab, and also the same with Professor devices in the IR group. So, and my research focuses on the AI for health, also AI agents, and multimodal visual language system. So I'm very excited to be here and have the chance to engage with this fantastic venue. So the topic I will be sharing is just show here the leveraging temporal images for biomedical radiology analysis. And actually, this is a piece of my work from earlier this year, and the topic is also the title of the paper. So this work is done with my three advisors, Zhang, Jake, and Adam. And so just a little brief, like transformer-based model have like a very increasing popularity in the recent year, and especially for the large language model. For like the auto-aggressive model, the capability able the transformer came from the transformer architecture, and that's very remarkable. So this is naturally raising another interesting question, like how can we extend this ability to the another modality and not just focus on the tasks. So also this work is seems like the title situated in the domain of the medical analysis, but actually the core technique, the core contribution of this model is more broadly to the multimodal representation learning and cross-modal alignment. So the idea behind of the label is just to enhancing the ability of the multimodal large language model to the process some temporal pair, which is actually particularly for the radiology report generation. And so there's just our today's talk. So first I will little brief introduce the background to go some classical models. Then I will touch into the domain-specific models along with a brief of radiology knowledge. And after that, I will talk about the motivation behind our work. Then I will walk with you through the more technology detail from the key component to the also the case study. I will show that. And finally, I will also share the code space, and you can try without this framework by yourself. And so let me first give you some background to help you better understand. So the first item I want to introduce is the visual language model. So even before the large language model becomes a widely used, there are also some model exist that can process both images, also the texts. So they are broadly defined. This kind of model cover two main research domain, computer vision, also the natural language processing. So obviously, more importantly, it's not just encoder model. It must contain some decoder part. So the visual language model are generative model and could generate some text or output because the decoder part is the language decoder. So one key of their strength is that the zero-shot generation. So they can easily adapt to another computer vision, also natural language processing task. So for example, it can be used to image recognition via detailed prompt, or question answering about the images, also documents understanding. So and so on. So in the past, this kind of task are often require some devices that retrieval-based method or classification neural networks or rule-based solution, build a whole system. But now you can use a single visual language model. We can handle all of these tasks and more flexible in the unified framework. And first of all, what is the multimodal large language model? So this is kind of new type of the generative model. So simply put, so this kind of model, the decoder part will be replaced by the large language model. And at the same time, the model can handle not only for the image information actually, but also can handle some other modality. So despite this differences, they are all the framework and follow the same architecture, like one modality encoder for the images, also for the video, and large language model as a backbone, also a connector in between of them, and link them in the latent space. And I will explain this component in more detail later. And of course, though, regarding the size of the parameter, actually the large language model will take the majority part of the total models of size. So, just this framework just show how the this kind of model merge the reasoning capability from the large language model, and also with the new ability to receive or reasoning, or you think about it, it's just a prototype of the ChatGPT like this way. And how this kind of model actually built. So in terms of the architecture, I said on the language side, they rely on the large language model. It can handle the decoding, also the generation of the final answer. But the key challenges is here, for the language model by default cannot process any other than texts actually. So because the tokenizer are designed only for the languages or sequence. So that is why we also need a connector, or you can say it's an adapter. Component just mapping the visual patch representation into the hidden space of the large language model, align their dimension, at least to align their dimension, so the model can process them together or simultaneously. So therefore, it's no longer imaging information or visual information to actually influence the generated task. So in terms of the training, actually, most of the model also share the same training object, which is just a regressive loss on the language output actually. And so be more specifically, so here is the example about the radiology example. So as shown here, it takes an images as an input along with the detailed or question related to this the single images. So and the model can generate the response. So actually, my research explore how to apply this kind of model to the radiology domain. So specifically for the chase X-ray, I'm not handle other CT scan or some other modality. So the setup is very simple here. Just chase X-ray as an input, and output will be generated a response based on the specific medical question, not just a normal question. And this kind of model can handle two classical tasks. One is the visual question answering. So where the model just receives the medical question and generate the short answer like here. And another task will be the report generation. So instead of giving the short answer, so the model must produce to generate the full medical report. So which normally require a more much deeper understanding of the whole chase X-ray. And so this is the task of my force. So let me introduce what is the radiology report. So this kind of report typically include several different sections, and the finding section, the most important will be the finding section, also the impression section. So the finding section will just key observation from the radiologist, while the impression section is kind of summarized of the doctor's conclusion or recommendation to the patients. So additionally, I have some other section like indication will be just provide some patients some history, but it's not our model to focus on. Our model focuses on the finding section and also the impression section. So let's talk about more detail on this kind of tasks. So it is very pretty straightforward, by the model takes a chase X-ray or paired chase X-ray or multiple chase X-ray and generate a corresponding report that can mimic how when the radiologists write their own report, like people. So here the key issue is most kind of model can only look at the single images in each turn. So which means they probably ignore some temporal information, temporal dimensions, whereas disease is getting better compared to the previous, or maybe it's getting worse, or just stay the same about some symptom. And so what is the temporal hallucination? And there are two classical examples. So for the single image cases, the model generate incorrect content, like here. The phrase is in comparison with the prior images studied, blah, blah, blah. So it's completely wrong because we don't give the model the specific prior scan or specific prior chest X-ray. The model hallucinated and make some incorrect reference to the non-existing prior studies. So this is the one hallucination. Another type will be the temporal image cases. So now we actually give the model two images or paired images. One is current, another one is previous, 2 weeks before the patient scan. And the model probably misinterrupt the temporal changes. Like the model here just states that the patient's some symptom is unchanged. But in the reality, for the ground truth, it's totally opposite. This kind of error these two types of error can be very dangerous especially for the clinical setting. So to fix this issue is our model aims to try. So you probably also wonder why does it happen? So the main reason is the data side bias. In the a clinical practical, the radiology always compare the previous scan when they writing the report. Even the patients came from another hospital, they won't take the previous scan, but will take the previous report to show the current radiologies. So naturally, the radiology rather the report often contains some comparison phrase like this one. So this means the temporal information always remains in the original data set. So and how can we handle this issue? One a common approach is to paraphrase the whole data set. You can use some tools, so you can use some expertise to do this manually. If you remove some temporal information, will force the model to ignore the whole temporal information entirely. So another approach is treating multi-images case a multi-turn conversation style, where the prior and current scan can be processed like a dialogue history. So at each turn, the model focuses on answering a question about the single images and generate the corresponding report for each images. So and finally, the model needs to summarize them together. And this may sound reasonable, but it relies heavily on the language model ability to distinguish different images and reason over the temporal relationship. And to addressing this, I just proposed a framework that can handle the paired image representation, allowing the model to fully utilize the temporal information rather than just ignoring this information. And like I said before, instead of relying on the prompt sequential tokens, which only operate at the shadow level, our method introduced temporal modeling directly to the multimodal models architecture. So embedding this kind of reasoning into the model's hidden split, we teach the model to handle this hallucination. So here is the overall architecture of the Libra. So you will notice that it's just follow the very classical structure visual encoder, also the connector, and also the large language model as a backbone. So actually, choosing the right pre-trained model is very crucial for the performance, especially in the medical domain. So especially we're using a Radiology is just a frozen biomedical image encoder, and medicine is another biomedical large language model. Both of them training on the specific radiology tasks. So in the ablation study, we confirmed that incorporating domain-specific pre-training model can boost the model further. So now let's talk about the connector actually. So here the model using the hyperstructure that combine the convolutional neural network and the transformer blocks, allowing to precise align the temporal features between the paired scan for each input. And actually, the one change in the real world setting in the dataset, it's not every scan have the prior study available, like I said before, to ensure a consistency between the training, also the inference. We introduced a simple but very efficient solution. It's just a dummy pair images, which just a copy of the current images if the previous scan not exist. This will help mitigate some suspicious inference to the non-existing scan and maintain the consistent input of the model for the training, also for the inference. So what doesn't matter is by modeling the temporal relationship at the architecture level, so this kind of model is more close to the real world setting actually. So for example, you can imagine that if the doctor sees some patient's condition remains stable, which means the current image scan and the prior chest X-ray are nearly identical. The doctor cannot see any difference between these two kind of images. So that's why we should align our models architecture. So the most important part is the temporal alignment connector. So it contains of the two key components. One is the layer-wise feature extractor. Another one will be the temporal fusion model. So the goal of the extractor is to aggregate multi-layer features from the image encoder. So you're probably wondering why not just why we need to use all hidden layers instead of just use a single one. Actually, you can have a global representation. So the first reason is even though the most model like the lava typically rely on the last or polytomial layer of the image encoder is enough, but that will focus on the global features. Actually, it's definitely will lose some information from the shadow layer. However, here we're using the 12 all hidden layers. It can help the model to capture the richer and multi-scale representation. So how does it work? You can imagine RGB channels work in the images, one image for the classical image encoder, the 3 channel can compress into a single unified representation. Here we're just treating the different layers as the channels to progressively compress them from the 12 layer to the single one, just using the simple convolution network to do some downsampling. So the first stage will give us fine grading the representation for the each images, for the current images, also from the previous images, also probably the dummy pair images. And pass to the temporal fusion model, now we need to actually combine the tell the model what's the difference between the current and the prior images. So so in this fusion model, it treats prior images as an auxiliary modality and apply some attention-based mechanism to integrate it to the current images. So this mechanism will ensure that the model understands the temporal difference instead of just concatenate the images them together in the latent space. So you can think about this. It's kind of like a current image during the training also inference always be the main query in the transformer blocks. So the current image will always be the main modality. So finally, we're using the multi-layer perception to align the feature dimensions with the large language space. And for the training, also it follows a very classical two-stage pipeline, which is widely used in this domain. So the first stage, we only train the connector and keep the visual encoder, also the large language model frozen. And the goal here is to just, we need to align the image features with the text space. There is a key tips in this stage, like in this stage, the data set must be as large as diversity as possible to make sure the connector is robust. Because like a well-trained connector is very crucial for this kind of multimodal large language model. And in the second stage, we fine-tuned on the specific tasks, focus on the report generation. Like I said, in the first stage, we'll probably using some like broad data set, maybe visual question answering, or just text conversation. And for the second stage, we just focus on report generation and just adding using the lower technique to the large language model and keep all the other components are frozen, both include the image encoder, also the connector. And this will make sure the large language model can still keep the following instruction ability, will not lose some information about the question. And about performance, actually, I will not go through detail. Like just overall, our result is like good performance across like a diverse evaluation metric, especially when compared with some similar size models. So, and finally, our model ranked actually the top 3 this year's it's a kind of open source leaderboard from the radiology report generation task. And it's actually verified by the third party like Biomedical school. They evaluate our model on the hidden evaluation data set. That's why our model didn't train on that data set. And here I think it's very interesting cases like corresponding to I said before the temporal hallucination type. And the first is a single image inference. So during the training, like our model can generate the report based only on the current images, focus on the image, current image, and without any useless information, especially for the temporal like phrase as compared blah blah. We don't have that information. And if we give the model with higher images as a reference, so the generated report will incorporate like a temporal phrase, like as compared to like simulating how the radiologists compare the scan with the retinal report. And the most interesting is like if we just swap the current and higher images, the generator will reverse its findings, like some worsening symptom will become improving. And for this case, just show like our model can understand the direction of the temporal changes rather than just memorizing the pattern of the input. That's I think is the most interesting cases in our case study. So that's all for my paper's detail. And so beyond technology detail about models, so if you believe like this kind of multimodal large language model can also apply to your research, and if you want to build your own multimodal large language model, so here is the repository, just a very easily starting point, because it's not limited to the radiology domain, and it provides a widely support for the different large language models, backbone and visual encoders, allowing you to customize the whole system wherever you like. And for the language model, actually this report can support Llama 2, also Llama 3, also Mistral, and even the smaller language model like Gima or Fini, supported by the Google. And for the visual encoder, and also it provides some clip, also the Dino, also the Signal. Yes, this one is very actually popular in the computer vision domain to extract the image features. So So, and most importantly, it's fully customized. Like I said, you can build your own visual towers and design your own connector. And also, my favorite part is beyond the loss matrix. Like the traditional way, you can only monitor the loss like during on the validation data side actually. So during the training, this report allowing to evaluate some like ALP matrix for your observation during the training. So as you also can define your own matrix and automatically save the best model checkpoint based on the validation performance. Another is like when the training, the model will automatically save the weight and support resulting from checkpoint in case of some like failures, like some like network is not there or something else. So, and also this report is fully compatible with our Unix cluster, so you can very easily to set up and run. And in addition, like I mentioned earlier, it's not limited to the radiology, and it also provides a very detailed data formatting guidance, so you can quickly prepare your own data set for the training. And there are also some like detailed training script for the training. Also the concatenate with different stages, the first stage or second stage. And they also have the online domain. Actually, you can just to show that how this model generation and a lot of features. And that's all for today's talk. So I hope you can get some inspiration for your research. And even though just it's a tools like here. So by the way, so the entire project I show is already open source, and actually I will continually updating with the latest model, latest technology. So yeah, that's all. Thanks for your listening.